Yes, sir.
Question 11. Yes.
Question 11 says what?
The integral of the 9 times square root of x all over x.
All over?
All over x.
Okay, we're integrating. Flare up here. Okay, so here's our plan in doing these integrals. If we've got the variable behind the minus sign, oh, that should be an a. We squared minus x squared. Variables behind the minus sign, then you take x to be a times the sine of theta. Don't forget its derivative. You have to replace each x and the dx with those two things there. And then eventually you'll use the fact that 1 minus sine squared of theta is going to be a cosine squared. If it's backwards the way this one is, the variable squared is in front of the minus sign, then our plan is to replace x with a times the secant of theta and replace dx with a times the secant of theta, tangent of theta, d theta. And eventually use the identity that secant squared of theta minus 1 is tangent squared. The other case was if you have a plus sign between the two terms, either in that order or the other order, doesn't matter when you're adding, then you replace x with a times the tangent of theta. And replace dx with a times secant squared theta, d theta. And then you'll eventually use the identity that tangent squared plus 1 is secant squared. You do those things, you should get an integral that doesn't have the radical sign. You should get a trig integral that you can figure out how to do. And then you get your antiderivative in terms of this trig integral and convert it back to x. So since this expression has the x squared in front of the minus sign, I'm going to use a secant. After we square that secant expression, I need the common factor of 4. So that means I'm going to take x to be 2 times the secant of theta. That goes in for each of these x's here. But for the dx, you got to take the derivative here. Put all of that in where the dx is. So I'm going to go ahead and square that. If the 9 doesn't matter. Let's go ahead and get the 9 outside the integral sign. And then I'm going to put 4 secant squared theta right here, 2 secant of theta here, and 2 secant theta tan theta d theta here. There's the 9. Here's the 4 secant squared theta, then the minus 4, all of that's under the radical sign. Then that's divided by x, which is now 2 secant of theta, and dx, which is 2 secant of theta, tangent of theta, d theta. I usually simplify that there radical sign, and then cancel, but you can cancel at this step if you want. You can cancel the two secant thetas right now. And then I'm going to factor out the 4 and get a secant squared theta minus 1 is the other factor. So I'm going to go ahead and cancel. And then I have that times the tangent of theta d theta. Here's where we use the fact that secant squared minus 1 is tangent squared. So now I have 4 tangent squared theta underneath the radical sign. That's what we wanted to do. Go from the difference of 2 squares to the product of 2 squares. When we have it in product form, we can take the square root of each term. So now I'm going to replace this with 2 tan theta. Take the 2 out there with the 9 and get an 18. Put those tangents together and get a tangent squared. Do you know a function whose derivative is tangent squared? Nope. So we don't know how to integrate this as it sits. The substitution I have for tangent squared is secant squared minus 1. Can you integrate both secant squared and the 1? I can help you integrate the 1. What would the integral of secant squared be?
Tangent.
Okay, so we can integrate both these parts. We make that change. Substitute this out for secant squared minus 1. Oops, I lost my 18.
Not just solve for tangent theta right there.
We couldn't think of anything whose derivative was tangent.
Solve for it.
You'll get back to this. We can integrate that. All right, so the integral of secant squared theta was tangent of theta. The integral of 1 is just theta. So now our antiderivative is in terms of theta. We need to get it in terms of x. So we go back here. Write that as x over 2 is equal to the secant of angle theta. So here's theta. The secant is the hypotenuse divided by the adjacent. So I make my hypotenuse length x and the adjacent length 2. And then we find the third side. 2 squared plus this length squared is x squared. Right? 2 squared plus b squared is x squared. Let's solve for b. B squared is x squared minus 4, so b is the square root of x squared minus 4. And if you've done these, then you know this radical always turns out to be one of the sides of the triangle. And now we want the tangent of that angle. So the tangent is opposite over adjacent. Opposite is the square root of x squared minus 4 over 2. Then you want theta. You can go from here and say theta is the inverse secant of x over 2. Or you can use the triangle and use whatever trig function you want. Sometimes Sometimes WebWorks says it won't take an arc secant. You might have to write it in terms of an arc cosine, an arc sine. But let's put that here. And that should be it. Yep, should be minus. Thank you. The 18 is multiplied with all of that in the parentheses. So what did you do differently? What part did you forget when you tried this?
Oh, yeah, I just didn't do the, I wasn't sure how to.
Yeah, you can just take the inverse trig function. Solve for theta here. Get one? Got a question?
I just have a question. This is, so for arc secant questions, like what percentage with all the Jackson hypotenuse, wouldn't that be the inverse secant? Just be the, right, so it's I'm not very good.
No, that would be the inverse cosine. It doesn't mean 1 over, it means inverse. So this doesn't mean 1 over. All right, the cosine of this angle is adjacent over hypotenuse. So if you wrote the inverse cosine of the adjacent over hypotenuse, then that would be theta.
Okay.
Yes, sir.
Can you integrate a tan cube?
Can I integrate a tangent cubed?
Yeah.
I can. It's just the pressure of his job. Integrating a tangent cube. Okay. So the point is, we can integrate a tangent to the first power. And tangent squared requires a substitution. So I bet a tangent cubed might need the same substitution. So let's try it. Integrate tangent cubed by first writing it as tangent times tangent squared, and see if this substitution works again for the tangent squared. That's what I do when I'm walking to school, is I do these integrals in my head. So if I get hit by a car, you'll know why, because I got stuck in a certain step.
Is this a tangent?
Does it matter?
I'm not thinking so, but I don't want to be wrong.
Let's do it next then. Let's integrate the tangent cube to this. And my suggestion was to write it as tangent times tangent squared. You know, when we're doing these trig integrals, we're always kind of thinking ahead for a du. If you've got a u as a tangent, what does a du look like? Secant squared, so I need to get a secant squared in there. And that's why I said this identity is going to come in handy. It's got a secant squared in it. So we make that change. Tangent squared is secant squared minus 1. But now I've got to break this up into two integrals, this one and that one. Tangent times the -1 is going to give me a tangent in here. So the first integral, do you see a u du?
Yeah.
There it is. That's just u to the first times du. U to be tangent of x. And then its derivative is the secant squared. So you're just integrating u du. And you get u squared over 2. The next one was a formula that I said maybe you could remember. And it's negative natural log of the cosine, right? So with that minus sign, I put a plus, the natural log of the cosine. We'll finally replace u with the tangent of x. And that should be the function whose derivative simplifies to tangent q. Okay. Another one from over. Wanted to do a one where we complete the square. Did we do one of those last time? It looks something like this, doesn't it? I don't know, was it a 1 over, 17 a 1 over? Did we do that one in class already? Okay. X squared plus 8x plus who? Plus 3. So I know this is a complete the square because it's not a UDU. I don't have an x to the first power term on top to take up the derivative of the stuff under the radical. So I can see it's not UDU, and it doesn't quite have the form of these because of this term. So I make it have the form of these by completing the square. Let's take the x squared plus the 8x. We're going to add a number here. We're going to take it back out, and then we're going to add the 3 that's already there. The number we're adding has to be a number whose two factors are identical and add to 8.
16.
16 has factors of 4 and 4. Right? Or you can always figure that out by taking half of the middle number and then squaring it, and that goes in here and in there. Half of 8 is 4, 4 squared is 16. Now the first 3 terms should factor as x plus 4 all squared. Do you agree? X plus 4 all squared. But then when I combine these two, I get a negative 13 on the end. So I got the difference of squares under the radical, and the variable is in front of the minus sign. So when the variable's in front of the minus sign, I take this stuff to be the square root of that number times the secant of theta. So we're going to take x plus 4 to be the square root of 13 times the secant of theta. See how it fits that? And now we need a dx term, so take the derivative of that line. The derivative of x plus 4 is dx. The derivative of this is the square root of 13 times the secant of theta, tangent of theta, d theta. Now let's substitute that in and see what it looks like. So x plus 4 all squared is going to be 13 secant squared. Then I have the minus 13 in the radical sign. The dx is this entire line here. Again and again and again. The easiest place to make the mistake is just forgetting to put the entire dx term in there. Dx doesn't automatically turn into d theta. Dx turns into trig function stuff times d theta. Okay, when I factor out the 13 here underneath the radical, I'm going to have 13 times secant squared theta minus 1. That's still under the radical sign, but secant squared theta minus 1 is tangent squared. So when I take the square root of that on the bottom there, I'll get a square root of 13. I'll also get a tangent that's on the bottom. I'll just move all this fraction stuff together. And you can see everything cancels but the secant of theta d theta. Is that one you remember? Okay, I'm going to use thetas. Natural log of secant of theta plus the tangent of theta. So we've got it integrated. Now we just get it back in terms of x. That's where we go back to our original substitution. From this line here, I can get that the secant of theta is x plus 4 over the square root of 13. I can also draw a triangle where that secant gives me hypotenuse over adjacent. The hypotenuse is the x plus 4. The adjacent is the square root of 13. The third side should turn out to be the stuff that's under the radical here. So this side over here is the x plus 4 squared minus 13. I need that third side because I got a tangent. Tangent is opposite over adjacent. So we fill that in right now and we'll be done. We'll have the natural log of, so instead of secant, we put in x plus 4 over radical 13. Plus tangent. Tangent is that square root of x plus 4 squared minus 13. And the adjacent side is square root of 13. Look out for completing the square if you've got an x to the first power in there. Okay? Now I'm going to ask you to do something really, really difficult. I want you to add 1/4 and 1/3. Give me a single fraction. 1/4 plus 1/3.
7/4.
How did you do that?
Once multiply.
Got a common denominator and you add them, right? 1/4 was 3/12. 1/3 was 4/12. 3/12 plus 4/12 is 7/12. We're going to do that problem backwards. My question will be, I have a fraction that's 7/12. What two fractions did I add to get 7/12? Well, you know the answer is 1/4 plus 1/3. But how can we figure that by going backwards? And we're going to take numbers out of it. We're going to put polynomial expressions in there. I added two fractions to get 1 over x squared minus 1. What two fractions did I add? So let two fractions add to 1 over x squared minus 1. I wonder if there's a lot of different fractions that would add to 5/12ths. Sure. 1/12 plus 4/12ths, 2/12 plus 3/12ths, 3/12 plus 4/12, blah, blah, blah. We get a lot of fractions that add to 7/12. Just find me any two fractions that add to 1 over x squared minus 1. Well, first think where you got the 12. You got the 12 by finding some common denominator between a denominator of 4 and 3. And the neat thing was 4 and 3 are relatively prime. They share no factors. So take a wild guess of two factors of x squared minus 1. An x plus 1 and an x minus 1, but maybe not a 1 on top, right? So we're going to guess an x plus 1 and an x minus 1 because those two would have that common denominator of x squared minus 1. Now, they don't necessarily have to have 1s on top, but they do necessarily have to have constants on top. I can't have a function of x here and add two improper fractions together to get a fraction in reduced form. I've got to have my fractions themselves in reduced form. So the numbers that go up here are just constants. So I'm going to make an algebra problem out of it. I'm going to say I need to know a constant for here and a constant for here so that when I add those two things together, I get this. So I'm going to now try to figure out the constants. I'm going to go ahead and get the common denominator. The common denominator is found by multiplying this fraction by x minus 1 over x minus 1, and multiplying this fraction by x plus 1 over x plus 1. So now I've got the x minus 1 times x plus 1 to multiply together to give me a common denominator of x squared minus 1. So I need all the stuff in the numerators on the right-hand side to add together and simplify to 1. So let's see. I've got x squared minus 1 and a 1 here. Over here, I have the common denominator, which is equivalent to x squared minus 1. So I'm going to share the denominators. I'm going to put the two numerators together. So let me multiply this out and get ax minus a plus bx plus b. I need that numerator on the right-hand side to equal 1. So it can't have any x's in it. Right, if I just regroup my terms so that you look at it this way. There's not any x's up here. So that says a plus b have to be two numbers that add to 0. So if that adds to 0, minus a plus b has to add to 1. So we have two equations and two unknowns. The first equation says that a has to be the opposite of b. So if I substitute that in here, I have the opposite of b added to b is equal to 1. So 2 times b is 1. That says b is a half. If b is a half and a is the opposite of b, a is a negative 1/2. So our conclusion is that I add negative 1/2 over x plus 1 to positive 1/2 over x minus 1 to get 1 over x squared minus 1. It's a bunch of algebra. I try to do it fast enough so I lose half of you. Did I lose anybody? Here's why we did it. My question now is, integrate this. I don't know. So I go over here to integrate that. I just integrate these. Can you integrate 1 over x plus 1? What is the integral of 1 over x plus 1? Natural log of the absolute value of x plus 1. So if I integrate here, I get negative 1/2 times the natural log of the absolute value of x plus 1. And integrate here, I get 1/2 times the natural log of x minus 1. That's our plan in this section. We're going to be asked to integrate some rational expression. If that rational expression's in reduced form, meaning the degree on top is strictly smaller than the degree on the bottom, then hopefully we can find several fractions that add together to give the initial fraction. And so to integrate the initial fraction, integrate the simpler fractions. If the fraction's not in reduced form, if the degree on top is not strictly less than the degree on the bottom, we have a step that we need to do first. What do we do when the power on top is higher or equal to the power on the bottom? Divide first. Always look to see if your fraction's in reduced form. Then we try to find factors, and then we see how we're going to add those together. With linear factors, it always behaves this way. Linear factor is x to the first degree. Always behaves this way so that you have constants in the numerator. So let's try another one. So to integrate, I want to integrate 7x plus 5 divided by x squared plus think here. So with an 8x minus I'm in trouble. Let's see if this works. To integrate that, let's try to find two fractions. Two. Oh. Two, maybe more, that add to this fraction. So the hard part of me making this example up was, are there any factors of 48, opposite in sign, that add to positive 8? 12 and 4. So I can factor the denominator to x plus 12, x minus 4, right? So I'm going to start that way. I'm going to say that my fraction inside is equivalent to that. So I'm thinking, kind of see here, that I had to add an x plus 12 with an x minus 4 to get that. So let's put something over x plus 12 and add it to something over x plus 4, x minus 4. Now this fraction is in reduced form. So these will also be in reduced form, which means I can't have x to the first powers up here. I just have to have constants. So again, I'm going to use letters A and B to denote those constants. And I'm going to try to do these steps again and find out what A and B are. I'm going to take some shortcuts. Been doing this algebra stuff for a long time. I don't want to put all these steps in there. Okay, so here's what I'm going to do. I'm going to take this rational equation and I'm going to multiply both sides by the denominator that's on the left-hand side. Is that okay with you? That'll clear all the fractions. If I multiply both sides by x plus 12 times x minus 4, I can clear all the fractions. So if I multiply this side by that, the denominators cancel, and I'm left with 7x plus 5. When I multiply this side by that, I distribute it to both fractions. So up here, I've got this multiplied by x plus 12 times x minus 5, and the x plus 12, x minus 4, and the x plus 12s cancel. So I'm left with a times x minus 4. If I take this and multiply here, the x minus 4's cancel, and I have b times x plus 12. Then I need the two numbers that multiply with the x to give me 7x on the left. And I need the constant terms to give me 5. So let me rearrange this. After I multiply it out, I'll have an ax plus a bx. So let me just write that as a plus bx. After I multiply this out, I have a negative 4a plus 12b. I have an x to the first power term, and I have a constant term, and they have to match up. So we're going to equate coefficients. On the left-hand side, the coefficient of x is a 7. On the right-hand side, the coefficient of x is a plus b. Then we have the constant terms. The constant on the left is a 5. The constant on the left is minus 4a plus 12b. So we have two equations and two unknowns. We can solve this by substitution or elimination, whatever you want to do. You have a favorite? Substitution from the first sentence, I can say A is equal to 7 minus B. Put 7 minus B right here. So that second equation will give me B. Do that kind of quick. You get negative 28 plus 4b plus 12b has to be equal to the 5. The 12b plus the 4b gives me 16b. Then I'm going to add 28 and 5, and I think I get 33. So B is 33 over 16. Kind of had to expect that since I just made this example off the top of my head. A is 7 minus B. Oops. And B is 33 over 16. Let's see, 7 times 16 is a big number. 112. $79 over 16 maybe is A. And so to integrate this, we just replace A and B with those numbers and integrate that. Let's see if we can do that in here. We have the integral of A, which is 79 over 16, divided by x plus 12, plus the integral of B, 33 over 16, divided by x minus 4. Both of those are logarithms without any constants being contributed. So we get 79 over 16 times the natural log of x plus 12, plus 33 over 16 times the natural log of x minus 4. That integral is the same as that one. Okay? So we replace a single fraction with several simpler fractions. But all we got to do is remember a set of rules. This was the distinct linear factor rule. Each factor is different. Well, sometimes not all the factors are different. Like for instance, what if you add 1 over x squared with 2 over x with 5 over x plus 1? What's the least common denominator?
X squared times x plus 1.
The least common denominator is x squared times x plus 1. This is an example of something that's a linear repeated factor. It's a power on x. It's possible that there's an x to the first power to give you a fraction that has an x squared times an x plus 1, but it's also possible that there's just 2 fractions that give you that. These 3 have that common denominator, and these 2 have that same common denominator. We're going to make this a repeated linear factor rule, that if we have something like this, suppose I have something like an x squared times an x plus 5 cubed with blah, blah, blah up here, some other stuff. If I want to try to find the partial fraction decomposition for this, I have to break it up into a total of 5 fractions that could possibly exist to have this common denominator. And here they are. It could come from something over x added to something over x squared, added to something over x plus 5, added to something over x plus 5 squared, added to something over x plus 5 cubed. That's the most general form of fractions that can have this as a common denominator. There can't be other fractions mixed in there. When I say repeated linear factors, whatever this power is, you've got to have that linear factor climbing until you hit that power. And since they're linear factors, you're going to guess constants up here. That's the repeated linear factor decomposition rule. Now, sometimes you're going to have a denominator that has a prime second degree factor. Prime means it can't be factored. For instance, I might have something like an x squared plus 4 as one of my factors. And maybe I'll have an x plus 2 down here. And I want to find the partial fraction decomposition of that. This is a linear factor. This is a prime second degree factor. If I had a minus sign between the x squared and the 4, I can factor it. But x squared plus a number is prime. The rule for breaking such a fraction up is you're going to have one fraction of each type. We'll have an x plus 2 and an x squared plus 4. But the numerators have to be 1 degree less than the denominator. So if I have a first degree denominator, I guess a constant up here. If I have a second degree denominator, I guess a general first degree factor up here, bx plus c. Sometimes if you are being hazed or something, you could have a prime third degree factor. They're harder to recognize which third degree factors are prime. But then if you were decomposing something up with a prime third degree factor, you guess a second degree, ax squared plus bx plus c. Always 1 degree less. Okay? We won't go much further than second degree factors. If I have a repeated second degree factor, suppose I had this to the second power, then I got to stick another feller over here with a different linear factor on top. Good thing there's 26 letters in the alphabet. I can keep going with capital letters up there. Okay? So the repeated factor rule applies to quadratic factors as well, but a quadratic factor needs a linear numerator. Yes, sir.
Why did you put plus C and plus E?
I need a general linear term like mx plus b, so I just kept going down the alphabet. Okay? So I'll do some examples of that next time, unless you guys want to stay for another hour. Those of you who fell asleep can stay another hour. Everybody else is putting their books together. This is prime nap time, isn't it? Prime nap time for 18-year-olds. Okay, we'll pick this up on Friday. Sorry? I will.
It was so